linking datasets on organizations using 500 million open collaborated records. Abstract. Scholars studying organizations often work with multiple datasets lacking shared identifiers or covariates. In such situations, researchers usually use approximate string fuzzy matching methods to combine datasets. String matching, although useful, faces fundamental challenges. Even where two strings appear similar to humans, fuzzy matching often struggles because it fails to adapt to the informativeness of the character combinations. In response, a number of machine learning methods have been developed to refine string matching. Yet, the effectiveness of these methods is limited by the size and diversity of training data. This paper introduces data from a prominent employment networking site, LinkedIn, as a massive training corpus to address these limitations. By leveraging information from the LinkedIn corpus regarding organizational name-to-name links, we incorporate trillions of name pair examples into various methods to enhance existing matching benchmarks and performance by explicitly maximizing match probabilities. We also show how relationships between organization names can be modeled using a network representation of the LinkedIn data. In illustrative merging tasks involving lobbying firms, we document improvements when using the LinkedIn corpus in matching calibration and make all data and methods open source. Introduction. As large datasets on individual political behavior have become more common, scholars have focused increasing attention on the methodological problem of linking records from different sources. Record linkage is an all-too-common task for researchers building datasets. When a unique identifier, such as a social security number, is shared between data collections and made available to researchers, the problem of record linkage is significantly reduced. Errors in linkage, presumably rare, may be regarded as sources of noise. In cases where unique identifiers like social security numbers are not available, recent literature has developed probabilistic linkage algorithms that can find the same individual in two datasets using stable characteristics such as birth year and race, or even mutable characteristics such as address. The rise of such techniques has paved the way for research that would have been costly or impossible to conduct in previous eras. These new techniques have had less of an impact so far on scholarship concerning organizational entities, such as corporations, universities, trade associations, think tanks, religious groups, nonprofits, and international associations, entities that are important players in theories of political economy, American politics, and other subfields. Like researchers on individuals, scholars studying organizations also seek to combine multiple data streams to develop evidence-based models. However, in addition to lacking shared unique identifiers, datasets on organizations also often lack common covariate data that form the basis for probabilistic linkage algorithms. Therefore, scholars must and do rely heavily on exact or fuzzy string matching based on names to link records on organizations, or alternatively, bear the significant costs of manually linking datasets. To take an example from the applied political science literature, Crossan et al. Compare the ideology scores of organizations with political action committees PACs to those without. Scores are calculated from a dataset of position-taking interest groups compiled by a nonprofit MapLight. The list of organizations with PACs comes from Federal Election Commission (FEC) records. MapLight and the FEC do not refer to organizations using the same names. There is no covariate data to help with linkage. The authors state that matching records in this situation is challenging P32, and consider both exact and fuzzy matching as possibilities. Ultimately, they perform exact matching on names after considerable preprocessing because of concerns about false positives, acknowledging that they do not link all records as a result. Indeed, the authors supplement the 545 algorithmic matches with 243 additional hand matches, implying that the first algorithmic approach missed about 1 in 3 correct matches. The challenge faced by Crossan et al. Is typical for scholars studying organizations in the US or other contexts. Given the manageable size of their matching problem, the authors are able to directly match the data themselves and bring to bear their subject matter expertise. In many cases, where the number of matches sought is not in the hundreds but in the thousands, practical necessity requires using computational algorithms like fuzzy matching, or hiring one or more coders, e.g., undergraduates or participants in online markets such as Amazon's Mechanical Turk. Both string matching and reliance on human coders have limitations. Even though string distance metrics can link records whose identifiers contain minor differences, They do not optimize a matching quality score and have trouble handling the diversity of monikers an organization may have. For example, JPM and Chase Bank refer to the same organization, yet these strings share no characters. Likewise, string matching and research assistants would both have difficulty detecting a relationship between Fannie Mae and the Federal National Mortgage Association. Such complex matches can be especially difficult for human coders from outside a study's geographic context, as these coders may lack the required contextual information for performing such matches. Methodologists have started tackling the challenges that researchers face in matching organizational records. Kaufman and Cleves, for example, propose an adaptive learning algorithm that does many different kinds of fuzzy matching and uses a human in the loop to adapt possible fuzzy matched data to the researcher's particular task. While this approach represents an improvement over contemporary research practices, an adaptive system based on fuzzy matching still requires researchers to invest time in producing manual matches and may also struggle to make connections in the relatively common situation where shared characters are few and far between, e.g. Chase Bank and JPM, or where characters are shared, but the strings have very different lengths, e.g. Fannie Mae and Federal National Mortgage Association. Scholars are also turning to large language models for performing name linkage tasks. However, these large language models have not been fine-tuned on match tasks, so they may struggle to produce matches similar to how fuzzy matching does. In this paper, we leverage a data source containing 500 million open collaborated records from the employment networking site LinkedIn, which can serve as a resource for scholars who seek to link records about organizations. We show how this dataset can assist in 3 distinct kinds of record linkage methods. The first approach based on machine learning, the second based on network analysis and community detection, and the third based on a combination of network and machine learning methods. Intuitively, each approach uses the combined wisdom of millions of human beings with first-hand knowledge of these organizations. Our argument is that this combined wisdom from trillions of real-world name pair examples can, if incorporated into a given linkage strategy, improve matching performance at relatively little cost. In what follows, Section 2 describes the massive training dataset we constructed from a scrape of LinkedIn. Section 3 describes how the LinkedIn data can be used to improve linkage given 2 distinct representations of the data stream. Section 4 illustrates the use of these linkage methods on 3 tasks revolving around the role of money in politics. Section 5 and Section 6 conclude. An open-source package, linkorgs, implements the methods we discuss. We make the massive LinkedIn name match corpus available in a Dataverse doi.org/10.7910/dvn/ehrqql. 2. Employment networking data as a resource for scholars of organizational politics. In this section, we explain how records created by users on LinkedIn, a leading professional networking platform, hold a wealth of information relevant for researchers studying organizational politics, particularly in the ubiquitous yet challenging task of assembling datasets. The key insight for the data asset we built is that LinkedIn users provide substantial information about their current and previous employers. For the sake of our illustration, we will use a near census of the publicly visible LinkedIn network circa 2017, which we acquired from the vendor datahut.co. Researchers do have the legal right to scrape this website and use the updated corpus as the Ninth Circuit Court of Appeals established in HiQ Labs Inc. v. LinkedIn Corporation, 2017. That said, these data do not come cheaply, and, informally, it seems to us that costs have increased as a result of greater investment in anti-scraping technology by site owners in the wake of the decision. Although we do not have a more recent scrape available to us at this time, there are vendors with more recent versions, e.g. using LinkDB. We expect over time that the approaches we take to the 2017 data will be applicable to later scrapes as they become available to the field. The dataset we use contains about 350 million unique public profiles drawn from over 200 countries, a similar size and coverage to LinkedIn's estimates reported during its 2016 acquisition by Microsoft. Footnote 1. To construct a linkage directory for assisting dataset merges, we here use the professional experience category posted by users. In each profile on LinkedIn, a user may list the name of their employer as a free response text. We will refer to the free response name or alias associated with Unit 1 as a I. In this professional experience category, users also often post the URL link to their employer's LinkedIn page, which we can denote as UI. This URL link serves as an identifier for each organization. Table 1. Table 2 provides descriptive statistics about the scope of the dataset as it relates to organizational name usage. The statistics reveal that, on average, users refer to organizations in about 3 different ways, and that, on average, each of the 15 million aliases links to slightly more than one organizational URL. The table also notes that there are more than 1,014 alias pairs. The database contains a large number of ways names can refer to the same or different organizational URLs. 3. Individual and ensemble approaches to record linkage using the LinkedIn corpus. We begin our discussion of how to best use the LinkedIn corpus with an example. Suppose we have 2 datasets, X and Y. X contains data about Wells Fargo Bank, JP Morgan Chase Bank, and Goldman Sachs. Y contains data about Wells Fargo Advisors, Washington Mutual, at one time a wholly owned subsidiary of JP Morgan Chase, and Saks Fifth Avenue. Ideally, manual linkage would successfully match Wells Fargo Bank with Wells Fargo Advisors, and perhaps even JP Morgan Chase Bank with Washington Mutual, while rejecting all other matches, including between Goldman Sachs and Saks Fifth Avenue, despite some passing phonetic similarity between the names. Figure 1 presents a checkered flag diagram illustrating our task. Names in the X dataset are on the left side. Names in the Y dataset are on the right. Each pair of names is represented by a node. To perform linkage, investigators apply an algorithm that assigns scores to all the nodes. They then consider a node to represent a match if it clears some numeric threshold, or alternatively, investigators can re-weight links in accordance with their match probability. There are many possible functions to score pairs. For example, exact matching scores each node as 1 if a I and a j are equal, 0 if unequal, accepting all pairs where the score is 1. In this example, exact matching would fail to link any of the organizations. The figure presents scores using the fuzzy matching approach, in this case, with the Jerzak metric. These scores present a familiar trade-off. If a cutoff of 0.7 is adopted, nothing matches. If 0.5% is selected, then Wells Fargo Bank successfully matches to Wells Fargo Advisors, but JP Morgan Chase Bank does not match to Washington Mutual. If a cutoff of 0.35 is selected, all the correct matches are included, but also several wrong ones. If a cutoff of 0.2 is selected, everything matches everything. There are no perfect options. The familiar trade-off facing researchers in this example comes about in part because the scores are too similar between pairs that we do and do not wish to match. Our focus is on algorithmic interventions that can produce scores that make it easier to distinguish between pairs that should match and those that should not at any particular cutoff. While ultimately we will propose an ensemble of 2 distinct approaches, we begin here by discussing the intuition underlying each. The first idea is that, to the extent that an algorithm trained on the LinkedIn corpus can reward similarities and latent meanings, e.g. bank and mutual, and punish dissimilarities, e.g. bank and avenue, it stands a good chance of improving upon existing character similarity methods. Machine learning approaches to this task are appealing, and we focus on applying these methods using the LinkedIn network. Despite the increasing sophistication of learning algorithms, these methods do have limitations, as the words in a name do not always have semantic value. Indeed, without specialized domain knowledge, it may be easy to miss matches between organizations having multiple acronyms. To account for this limitation, an approach that utilizes community detection algorithms is desirable and complements the first approach by leveraging alias to URL links more explicitly. We provide more details on each approach below and conclude by describing how to unify them in an ensemble. Machine learning approach. Machine learning continues to make so many advances that it is becoming hard to choose, let alone justify as best, any particular framework. The future will no doubt yield improvements in any machine learning approach for modeling name match probabilities, as the rapid progress in large language models has made apparent. That said, to make progress we need to make and explain our choices. We set up the machine learning problem as the task of learning a function, fn, that maps a textual alias, a, to a point in a high-dimensional real-valued vector space. The distance between 2 aliases, a and a, is to be calculated as orf-na, fnar. We are mindful that one major benefit of learning a map from the space of strings to numerical vectors is faster matching. String similarity algorithms, such as the Jerzak algorithm, typically require an operation on each combination of entries that one wishes to match in sets X and Y. The calculation of a single score can be quite time-consuming. By contrast, applying fn to all the entries of x and y generates two sets of points in a vector space. Calculating a distance between all pairs of points is typically a much faster computation than the equivalent string distance calculation on all the pairs. The function, fn, that our algorithm will learn is, to a degree, a black box. It optimizes over many parameters by seeking to best fit some target outcome. Hence, the way we structure the target influences the ultimate algorithm we produce. Perhaps the simplest approach to setting up an outcome would be to look at the set of all alias pairs and assert that two aliases are linked if two people used those aliases to refer to the same URL, and not linked if no one ever did. A limitation of this lookup table-like approach is that it has no sensitivity to the number of links in the data, so a person who mistakenly writes Goldman Sachs as their employer and links to the Sachs fifth page would get equal weight to the much more common case where employees write that they work at Goldman Sachs and link to the Goldman page. Incorporating information about the relative number of links is clearly desirable, but requires care. As a starting point, we borrow ideas from naive Bayes classifiers to calculate a probability that two aliases are indeed true matches using the depth of ties between links. In section AI11, we explain assumptions that would allow the interpretation of this outcome variable as a probability, written as y sub ij equals the probability of I and j match, given a sub I equals a and a sub j equals a prime, equals the sum over all u, in the set u of the probability of u sub I equals u given a sub I equals a multiplied by the probability of u sub j equals u given a sub j equals a prime. To explicate this formula, note that for each URL u, the term capturing the probability of u sub I equals u, given a sub I equals a multiplied by the probability of u sub j equals u, given a sub j equals a prime, reflects the proportion of occurrences of u given alias a times the proportion of occurrences of u given the alias a. As an illustration, consider a profile URL, like linkedin.com/company/Wells Fargo, and the two aliases, JP Morgan Chase Bank and Wells Fargo Advisors. Whenever JP Morgan Chase Bank is used, it generally occurs with a different company profile, so this particular URL contributes little to the overall probability, even though Wells Fargo Advisors almost always links to this particular profile URL. By contrast, if Wells Fargo Bank and Wells Fargo Advisors both typically link to this same profile page, then the probability of a match will be calculated as high. The overall loss function we seek to minimize is defined next. Loss equals the sum over I sum over j of KL of y hat sub ij comma y sub ij, where the KL divergence computes the distance in probability space between y hat sub ij, the predicted match probability, and y sub ij, the match probability as computed using the LinkedIn corpus. We now discuss how we structure the f sub n function that ultimately generates y hat sub ij. For details, see section. Our approach builds from work on the vector representations of words. Mikolov et al., 2013. In our case, we build a model for organizational name matches from the characters on up. Figure 2 provides an illustration of the model's structure. In particular, we model each character as a vector, with each dimension representing some latent quality of that character, each word as an ordered sequence of character vectors, and each organizational name as an ordered sequence of word vectors learned from their character constituents. That is, first we learn a good representation of words based on ordered characters. Then, we learn a good representation of organization names based on ordered words. Finally, we repeatedly optimize the system through backpropagation to minimize the loss function above. Here, an important parameter is the dimension of the vector representation. We adopt a 1024-dimensional numeric representation of organizational names, balancing computational efficiency with informational richness. Similar to other word embedding approaches, each dimension of the ultimate vector has a latent semantic value, although that value may be hard to interpret. In Figure 3, we examine how the algorithm has mapped aliases into the embedding space. Due to the difficulties of visualizing multidimensional data, we project the alias embedding space down to 2 dimensions via principal component analysis, PCA. Pairs of aliases representing the same organization are represented by the same graphical mark type. We see that aliases representing the same organization are generally quite close in this embedding space. The model seems to be able to handle less salient information. Well, Oracle and Oracle Corporation are quite close in this embedding space, even though the presence of the long word corporation would substantially affect string distance measures, based only on the absence of discrete letter combinations. While researchers may drop common words like corporation based on intuition, our optimized model learns which words to emphasize or ignore from data. While these examples are interesting and encouraging, they do not present a particularly rigorous test of the algorithm's performance. In Figure 4, we examine how well names that should match do match, and how well names that should not match do not match according to the estimated model. In particular, we hold out from training 2,000 randomly chosen pairs of aliases sharing a URL, matches, and 2,000 randomly chosen pairs of aliases where a URL is not shared, non-matches. For the set of matches and non-matches, we provide density plots of the match quality under fuzzy matching and under our learning model. The right panel of Figure 4 considers predicted match probabilities for the out-of-sample set of match and non-match examples from the LinkedIn corpus. In particular, it shows density plots of the predicted probabilities of pairs that are matches and, separately, non-matches. If the algorithm is working as it should, then the overall distribution of match probabilities for matches and non-matches should differ greatly. Indeed, this is what the figure finds. A KS test for assessing whether the probabilities are drawn from the same distribution yields a test statistic of 0.87 p less than 1016. A statistic of 0 indicates complete distribution overlap, while 1 signifies perfect separation. Encouragingly, we are closer to this second case. The left panel shows results with Jerzak distance fuzzy matching, which yields KS test statistics ranging from 0.47 to 0.55. Depending on the character Q-grams used. Despite these successes, there are true links that would remain hard to model using this prediction-oriented framework. For instance, the aliases Chase Bank and JP Morgan have a low match probability. To handle such cases, we next show how the LinkedIn data introduced in this paper can be used in a network-oriented approach to improve organizational record linkage. 3.2 Network-based linkage algorithms with LinkedIn data. As we have already seen, organizational names sometimes contain little semantic information. As a result, methods that focus on uncovering these meanings have a ceiling. Often, the relationship between two aliases for an organization is something that one simply has to know. The question then is how to best leverage the knowledge implicit in the LinkedIn network, bearing in mind that the raw data may not reveal the full depth of knowledge in the network. Instead of viewing the record linkage task as matching two lists of organization names directly, one can instead view it as connecting these names on a graph. A tricky point, of course, is that the names of the organizations in one's lists may not actually be on the graph. We address this issue below when thinking about an ensemble strategy, and also through our third application. But even assuming the names are on the graph, one must consider the sense of connectedness that is most useful. The simplest concept of connectedness would assert that two aliases are linked if someone has attributed the same URL to both names. This notion would often fail to follow transitivity. In other words, if A and B refer to the same organization and B and C refer to the same organization, then A and C should refer to the same organization. But, despite this, they may not share a URL. So, without care, we may miss this connection. It is tempting then to insist on transitivity in alias names. Implicitly, doing so casts the problem of record linkage as placing an organization in a particular connected component of the LinkedIn network. An issue here is that, if there are spurious links, then many components will be merged where there is little evidence to support such an action. An approach that is in between, allowing for some transitivity when the evidence is sufficiently strong, but not when the evidence is weak, is desirable. Community detection methods aim to find this sweet spot. Because community detection is a well-studied problem that occurs in many applied contexts, we consider two algorithms established in the methodological literature, Markov clustering and greedy clustering. We focus on these algorithms because they model the network in distinct ways and are computationally efficient. Implementation details are an appendix to second. Here, we offer a brief sketch of each. Figure 5 shows how we can represent the data source explicitly as a network for Markov clustering. Here, 11 organizational aliases are presented as nodes. Aliases are connected by edges. In principle, these could be directed or undirected, weighted or unweighted, depending on one's modeling strategy. The figure shows edges with weights that follow a naive Bayesian strategy for calibrating the amount of information between names. We use a similar probability calculation as in equation 1. Under this approach, the probability that A and B is connected is the same as the probability that B and A are connected. Therefore, this yields a weighted, undirected graph. Notable, we see the strong ties where the connection is surprising based on semantic information, such as Chase and Washington Mutual. Visually, it is clear that there are 2 to 3 clusters where links are denser, but there are also occasional ties across the clusters that ex ante are hard to identify as spurious or real. These clusters of nodes with relatively dense connections are the community of aliases we wish to discover. Markov clustering applies arithmetic operations to the edges of the graph that alternately diminish weak links in the graph and enhance strong ones. The middle panel of Figure 5 shows the partial completion of this algorithm, while the right panel shows it at convergence, where each organization is placed in a single community, identified by the alias most prominent in it. For example, JP Morgan Chase and Bank of America. In contrast to Markov clustering, greedy clustering is an iterative algorithm that begins by assuming each node is its own community, and then merges communities that would result in the largest increase in the overall quality of the network structure. We use one of the most ubiquitous quality measures called a modularity score. This score is 0 when community ties between aliases and URLs occur as if communities were assigned randomly. It gets larger when the proposed community structure places aliases that tend to link to the same URLs in the same community. While the Markov clustering algorithm requires edges to have probability weights, greedy clustering does not, which enables community detection with a bipartite as opposed to adjacency representation. Ultimately, we find somewhat better performance with this bipartite representation of the LinkedIn network, where the names and URLs are both considered nodes and the links only occur between names and URLs if there is an attribution in the LinkedIn database, with edge weights given by the number of times 2 attributions are made. 3.3 Joint network and prediction-based record linkage using the LinkedIn corpus. The LinkedIn calibrated machine learning model uses complex semantic information to assist matching but does not make use of graph theoretic information. The network-based methods use network information but do not use semantic information to help link names in that network. To get the best of both worlds, we propose a third unified approach that uses both the semantic content and graph structure of the LinkedIn corpus. The unified approach is an ensemble of both network and machine learning methods and involves 3 steps. Figure 6 returns to the example at the beginning of this section involving the merge of a dataset about Wells Fargo Bank, JP Morgan Chase Bank, and Goldman Sachs X, with another dataset about Wells Fargo Advisors, Washington Mutual, and Saks Fifth Avenue. The figure presents several checkered flags illustrating the multi-step approach. In Step A, machine learning-assisted name linkage is directly applied between the 2 datasets. Similar to fuzzy string matching, scores are calculated on the cross product of 2 sets of names. Scores exceeding a threshold set to 0.5 in the figure are said to match. In this particular example, fuzzy matching could produce similar results, but the thresholds and scores would differ, and, as a result, so too would performance. In Step B, machine learning-assisted name linkage is applied to an intermediary directory built using community detection. We attempt to place X in their proper community and Y in their proper community, and then we consider entries in X and Y as linked if they are placed in the same community. This example shows how the unified approach can put to use the potential of both methods presented thus far. Through Step A, it can link datasets for organizations that do not appear on LinkedIn, but whose naming conventions are similar. Through Step B, the unified method picks up on relationships that are not apparent based on names and require specialized domain expertise to know. We now turn to the task of assessing how these different algorithmic approaches and representations of the LinkedIn corpus perform in examples from contemporary social science. Evaluation tasks, method evaluation. Before we describe the illustrative tasks, we first introduce our comparative baseline and evaluation metrics. This introduction will help put the performance of the methods into context. Fuzzy string matching baseline. We examine the performance of the LinkedIn-assisted methods against a fuzzy string matching baseline. While there are many ways to calculate string similarity, we continue to focus on fuzzy string matching using the Jacquard distance measure to keep the number of comparisons manageable. Other string discrepancy measures, such as cosine distance or edit distance, produce similar results. a machine learning baseline. We also examine the performance of the LinkedIn-assisted methods against a machine learning baseline, DZ match, that uses a recurrent neural network-based fuzzy matching approach outlined in Hosseini et al. With hyperparameters left at their defaults, this approach will provide a helpful baseline for contextualizing performance. A network approach baseline. We also examine performance against a simple method, hereafter lookup, that uses the LinkedIn data as a giant lookup table for organizations to assess the relative value added of the clustering algorithms. In this approach, we consider two aliases as matched if they link to the same URL, at least once in the LinkedIn corpus. Performance metrics. We consider two measures of performance. First, we consider the fraction of true matches discovered as we vary the acceptance threshold. This value is defined to be the number of true positives found divided by number of true positives in total. This measure is relevant because, in some cases, researchers may be able to manually evaluate the set of proposed matches, rejecting false positive matches. The true positive rate is therefore more relevant for the setting in which scholars use an automated method as an initial processing step and then evaluate the resulting matches themselves, as may occur for smaller match tasks. While the true positive rate captures our ability to find true matches, it does not weigh the cost involved in deciding between true positives and false positives, i.e., matches the algorithm finds that are not in fact real. Failure to consider the costs of false positives can lead to undesirable conclusions about the performance of algorithms. Everything matches everything is a situation that ensures all true matches are found, but the results are not informative. Given such concerns, we also examine a measure that considers the presence of true positives, and false negatives known as the F-beta score, defined as 1 plus beta squared times true positive divided by 1 plus beta squared times true positive plus beta squared times false negative plus false positive, where the beta parameter controls the relative cost of false negatives compared to false positives. In the matching context, errors of inclusion are typically less costly than errors of exclusion. The list of successful matches is easier to double-check than the list of non-matched pairs. For this reason, we examine the F2 score, a choice used in other evaluation tasks, e.g. Devaria et al., which weighs false negatives more strongly than false positives. 4.1.5. Comparing algorithm performance across acceptance thresholds. Approximate matching algorithms have a parameter that controls how close a match must be to be acceptable. Footnote. 3-2 algorithms might perform differently, depending on how the acceptance threshold parameter is set. This threshold is not directly comparable across algorithms. For instance, a change of 0.1% in the match probability tolerance under the ML algorithm implies a much different change in match dataset size than a 0.1% change in the Jacquard string distance tolerance. To compare the performance of these algorithms, our figures and discussion focus on the size of matched datasets induced by an acceptance threshold. The most stringent choice produces the smallest dataset, i.e., consisting of the exact matches, while the lowest possible acceptance threshold produces the cross product of the two datasets, i.e., everything matches everything. Between the two, different thresholds produce datasets of different sizes. By comparing performance across matched dataset sizes, we can evaluate how the algorithms perform for different acceptance thresholds. 4.2 Task 1. Matching performance on a lobbying dataset. We first illustrate the use of the organizational directory on a record linkage task involving lobbying and the stock market. Libgober shows that firms that meet with regulators tend to receive positive returns in the stock market after the regulator announces the policies for which those firms lobbied. These returns are significantly higher than the positive returns experienced by market competitors and firms that send regulators written correspondence. Matching meeting logs to stock market tickers is burdensome because there are almost 700 distinct organization names described in the lobbying records, and around 7,000 public companies listed on major U.S. exchanges. Manual matching typically involves research on these 700 entities using tools such as Google Finance. While the burden of researching 700 organizations in this fashion is not enormous, Libgober only considers meetings with one regulator. If one were to increase the scope to cover more agencies or all lobbying efforts in Congress, the burden could become insurmountable. Treating the human-coded matches in Libgober as ground truth, results show how the incorporation of the LinkedIn corpus into the matching process can improve performance. Figure 7 shows that the LinkedIn-assisted approaches almost always yield higher F2 scores and true positives across the range of acceptance thresholds. The highest F2 score is over 0.6, which is achieved through the unified approaches, the machine learning approach, and the bipartite graph-assisted matching. The best performing algorithm across the range of acceptance thresholds is the unified approach using the bipartite network representation when combined with the distance measure obtained via machine learning. The percentage gain in performance of the LinkedIn-based approaches is higher when the acceptance threshold is closer to 0, as we increase the threshold so that the match dataset is 10 or more times larger than the true match dataset. The F2 score for all algorithms approaches 0, and the true positive rate approaches 1. For illustration, let us examine a case where it successfully identifies a correct match that fuzzy matching fails to detect. Fuzzy matching fails to link the organizational log entry associated with HSBC Holdings plc to the stock market data associated with HSBC. Their fuzzy string distance is 0.57, which is much higher than the distance of HSBC Holdings plc to its fuzzy match 0.13 for AMC Entertainment Holdings Inc. HSBC Holdings plc, however, has an exact match in the LinkedIn-based directory, so the two organizations are successfully paired using the patterns learned from the LinkedIn corpus. Another relevant consideration in applied matching tasks is compute time. In section A, 6.1.1, we document the runtime of each approach in the different applications. As expected, the network-based approaches have the greatest computational cost, as some measure of distance between each candidate observation must be computed against all of the hundreds of thousands of entities in the LinkedIn corpus. For these network approaches, the runtime is on the order of several hours for this roughly 700 by 7,000 name merge. By contrast, fuzzy matching runs in less than 1 minute. The machine learning approach without the combined network approach runs in roughly 5 minutes on 2024 hardware. Scaling the best methods is, therefore, a potential concern as one reaches datasets with organizations numbering in the tens or hundreds of thousands. Back-of-the-envelope calculations suggest that a 10,000 by 10,000 organization match would potentially have a 2 to 3 day runtime using full bipartite ML, which is long but not unacceptable. As is it performed once in the course of an entire project without much researcher intervention. Additional strategies would likely be necessary to scale to a 100,000 by 100,000 name matching problem. As the best performing, but slowest, algorithm would run somewhere around 255 days. A wait time not realistic for the research iteration process. Two such strategies are parallelization and locality-sensitive hashing. While parallelization can speed up easily subdivided problems like name matching, most computational costs are spent checking pairs that have low match probabilities. Techniques such as locality-sensitive hashing can improve speed by avoiding comparisons between unlikely matches. Overall, the results from this task illustrate how the LinkedIn-assisted methods appear to yield better performance than commonly used alternative methods, such as fuzzy matching. In the ubiquitous use case when researchers do not have access to shared covariates across organizational datasets. Task 2. Linking financial returns and lobbying expenditures from Fortune 1000 companies. In the next evaluation exercise, we focus on a substantive question drawn from the study of organizational lobbying. Do bigger companies lobby more? Prior research leads us to expect a positive association between company size and lobbying activity. Larger firms have more resources that they can use in lobbying, perhaps further increasing their performance. Our reason for focusing on an application where there are such strong theoretical expectations is to illustrate how results from different organizational matching algorithms can influence one's findings. Something that would not be possible without well-established theory about what researchers should find. For this exercise, we use firm-level data on the total dollar amount spent between 2013-2018 on lobbying activity. This data has been collected by Open Secrets, a nonprofit organization focused on improving access to publicly available federal campaign contributions and lobbying data. Open Secrets 2022. We match this firm-level data to the Fortune 1000 dataset on the largest 1,000 U.S. companies, where the measure of firm size we focus on is the average total assets in the 2013 to 2018 period. The key linkage variable will be organizational names that are present in the two datasets, that is to say, the name of the company according to Fortune and according to Open Secrets. we manually obtained hand-coded matches to provide ground truth data. In Figure 8, we explore the substantive implications of different matching choices, how researchers' conclusions may be affected by the quality of organizational matches. We see that the coefficient relating log organizational assets to log lobbying expenditures using the human match data is about 2.5%. In the dataset constructed using fuzzy matching, this coefficient is underestimated by about half. The situation is better for the datasets constructed using the LinkedIn-assisted approaches, with the effect estimates being closer to the true value. For all algorithms examined in Figure 8, there is significant attenuation bias towards 0 in the estimated coefficient as we increase the size of the matched dataset, as poor quality matches inject noise into estimation. Overall, we see from the right panel that match quality depends on algorithm choice, as well as string distance threshold, with the LinkedIn-based approaches capable of estimating a coefficient within the 95% confidence bounds of the ground truth estimate. Fuzzy matching and DZ match, at their best, find an estimate that is only half as large in magnitude as the true value. Task 3. Out-of-sample considerations, merging eCombinator and PPP data. A final question is about how these methods perform in out-of-sample testing, which is performed with organizations that we do not expect to be well represented in the current version of the LinkedIn data for whatever reason. While our methods could be adapted to use more recent versions of the LinkedIn data from 2017 cannot directly describe organizations that did not exist then. In this task, we analyzed data from the period after the main data collection took place, in an effort to understand the strengths and limitations of the various linkage strategies in this context. Here, we first examined data from a eCombinator directory on incubator startups. The dataset contains a collection of startups involved in the eCombinator seed funding program, detailing their name, website, business model, team size, and development stage. This data provides a snapshot of the company's early progression, from inception to public trading or acquisition. The eCombinator program was launched in 2005. For a purer out-of-sample test, we subset the data to the 2017-2024 period. We merged these startups to the Paycheck Protection Program PP loan database. The PP 2020-2021 was a program aimed at providing financial relief to businesses during the COVID-19 pandemic. The dataset includes entries with key financial metrics, such as loan amount, approval date, borrower name and address, and employment impact. The task of matching startups to the PPP loan data could be relevant for evaluating the role of these loans on long-term firm survival, as well as for thinking about the regulatory advantages that come from affiliation with a business network like eCombinator. Importantly, none of these covariates overlap with the Y Combinator data. We subset both sets of data to target businesses within the San Francisco area. As expected, we find in Figure 9 that the linkage approach is only using the directory of firms with established LinkedIn pages, as of 2017, provide no gain in the overall F2 score relative to fuzzy matching. If these methods were rebuilt with a subsequent scrape of the LinkedIn database, they would likely do better with these new organizations. That said, the machine learning approach still provides a boost over fuzzy matching. The approach has inferred more enduring information about the link probability between companies based on the semantic content of names. 5. Discussion, limits and future of the LinkedIn data in improving record linkage. We have shown how to use 500 million user-contributed records from a prominent employment networking site to help link datasets about organizations. Researchers studying organizations frequently find themselves in situations where they must link datasets based on shared names and without common covariates. Existing methods, notably human coding and fuzzy matching, or some combination of the two, are costly to apply and often involve ad hoc decision-making by scholars about what seems to be working well or well enough. We have shown how the LinkedIn corpus can be used, either via machine learning or network detection, to improve organizational record linkage. These approaches are summarized in Table 4. These results may have implications for applied work. In our second application, the choice of record linkage method is consequential for the ultimate regressions that one runs and intends to present to other scholars. Using a unified approach, we were able to estimate a coefficient of theoretical interest within a 95% confidence interval using ground truth. Using other methods, particularly fuzzy matching, we were unable to recover the coefficient of interest. Although the sign was correct, the magnitude was statistically and substantively different. Typically, Scholars do not have access to ground truth, and, therefore, will not have a sense of how well or how badly they are doing in the aggregate. This is a potentially serious problem affecting research on organizations. However, we do not believe that this application alone should cast substantial doubt on what scholars have been doing. Typically, researchers use a mix of hand coding and automated methods, and we expect that this kind of approach will do better than a purely automated approach, especially one relying on string distance metrics alone. For linkage problems that are too big for mixed workflows greater than 105 observations, the work here suggests it is important to test sensitivity to linkage and hyperparameter choice. We provide some examples of how that might be done. While the integration of the LinkedIn corpus here would seem to improve organizational match performance on real data tasks, there are many avenues for future extensions, in addition to those already mentioned. First, to incorporate auxiliary information and to adjust for uncertainty about merging and post-merge analyses, probabilistic linkage models are an attractive option for record linkage tasks on individuals. In such models, a latent variable indicates whether a pair of records does or does not represent a match, inferred via expectation maximizing using information about the agreement level for a set of variables, such as birth date, name, residence, and, potentially, employer. Information from these LinkedIn-assisted algorithms can be readily incorporated into these algorithms for estimating match probabilities on individuals. The methods described here might also incorporate covariate information about companies. For instance, researchers can incorporate such information in the final layer of the LinkedIn-based machine learning model and retrain that layer using a small training corpus. This process, an application of transfer learning, enables extra information to be brought to bear while also retaining the rich numerical representations obtained from the original training process performed on the massive LinkedIn dataset. Finally, the approaches here are complementary to those described in Kaufman and Cleves, and it would be interesting to explore possible combined performance gains. Conclusion. Datasets that are important to scholars of organizational politics often lack common covariate data. This lack of shared information makes it difficult to apply probabilistic linkage methods and motivates the widespread use of fuzzy matching algorithms. Yet fuzzy matching is often an inadequate tool for the task at hand, while human coding is frequently costly, particularly if one wants human coders with the specialized domain knowledge necessary to generate high-quality matches. We have introduced a novel data source for improving the matching of organizational entities using 500 million open collaborated employment records from a prominent online employment network. We show how this data can be used to match organizations that contain no common words or even characters. We validate the approach on example tasks. We show favorable performance to the most common alternative automated method, fuzzy matching, with gains of up to 60%. We also illustrated how increased match quality can yield improved substantive insights and better statistical precision and predictive accuracy. Our primary contribution to the research community is providing a data source that can, in ways explored here and hopefully refined in future work, improve organizational record linkage while using this unique and useful corpus.